All right, we're going to look at some of the solutions to our test review for our third test covering Chapter 4. So the first thing we have here is we are talking about graphing exponential and logarithmic functions, stating the domain and range, and finding the asymptotes. So the key thing to remember is we start with some base function for these. So we'll start with some base to a power of x or some log of base b to some power x. So in general, if you recall, for an exponential function, we always have three key points on this graph: -1, 1 over b, 0, 1, and 1 comma b, with a horizontal asymptote of y equals 0. So those are always base functions on any exponential graph. So if we consider this one, we have 3 times 2 to the x minus 1. Our base, or our parent function, our starting function, is going to just be 2 to the x. Now why that's important is that's going to give me some starting points to start from. So if I hop down here, I know my starting points are just these key points, but instead of b, I'll just put 2. So we have -1, 1/2, we have 0 and 1, and we have 1 and 2. So that would be for just this graph 2 to the x with a horizontal asymptote of y equals 0. Now obviously our graph is not that, it's going to be changed somehow, so we're going to have to do basic transformations to see how this thing moves. So if I look at our function, on the inside of the function, remember inside is up here in the x, I see x minus 1. So an x minus 1 is going to shift that to the right 1. So all of my x's will get increased by 1. So we'll write that down there here. And then on the outside, I see I have a multiply by 3 and a subtract 4. So everything on the outside, I have times 3 minus 4. So my rule for the y's are going to be 3y minus 4. So I can use these points I had down here, these key points, I'll zoom in over here, to get my new points. So my new points on the graph, I'm going to obviously first take the x's and add 1. So that's going to be 0, 1, and 2. Okay, that's pretty simple. Now for the y's, I'm going to multiply by 3 and subtract 4. So if I take 3 times 2, it's 6. I'm just going to do that one first. 3 times 2 is 6. 6 minus 4 is 2. This one is 1. 1 times 3 is 3. 3 minus 4 is -1. Half times 3 is 1.5. And 1.5 minus 4 is -2.5. I also want to look at this asymptote. It's 0. But that will change because if I multiply 0 by 3, I get 0, but 0 minus 4 will be -4, so my new horizontal asymptote will be at -4. And this is sufficient information to graph it. Now obviously on the test you have access to a graphing utility, you can check this and get a lot of these points, but I want to show you how you would do it by hand using the key points on our graph. So now if I want to pop up here, I can graph it and kind of see what it looks like. So I know it's going to have a horizontal asymptote at -4. So it's going to look something like that. We're going to have points at 0, -2.5. That's that point there. 1, -1 is there. And 2 is going to be there. And since this graph has to kind of approach this asymptote and do some kind of exponential growth, it's going to look something like that. So based on my points, that is going to be the graph of 3 times 2 to the x minus 1 minus 4. So just remember these key points when you're graphing it, okay? The other thing it wants is the domain and range. That's fine. Remember for an exponential problem, domain is always -infinity to infinity because it's going to go left and right as far as you want. And range is how low it goes to how high it goes, so the range is going to be -4 to infinity. All right, let's look at an example of a log. This one says log of 2x plus 1 minus 2, which is a little harder than I wanted to do, so I think I might change this problem. I think I'll change this one to just log of x plus 1 minus 2. Otherwise, you're going to get into some pretty tricky stuff with the dilation and the shift. So let's just do this one. So remember, the key points for a log are going to just be the flip of the exponential. So 1 over b, negative 1, 1, 0, and b, 1. And this is going to have a vertical asymptote of x equals 0. So our parent base function in this one is simply just going to be log of x. So that's giving me a base of 10. So my key points will simply be 1/10 and negative 1, and 1 and 0, and 10 and 1. So now if I look at what my transformations are, I've got x plus 1 here and minus 2 here. So the x plus 1 inside is going to shift it left by 1. And then the minus 2 on the outside is going to shift the y down 2. Now I also probably want to make sure I'm looking at what happens to my x equals 0, because obviously my x equals 0, when I shift it left, 0 minus 1 is going to make this negative 1, x and y. So I'm going to subtract 1 from all the x's, so negative 9/10, 0, and 9. And then we'll do the same thing with the y's, except we'll subtract 2. So negative 3, negative 2, and negative 1. So my vertical asymptote now that I got some points, my vertical asymptote is going to be at negative 1. Something like that. Negative 9/10, negative 3, 0, negative 2, and then 9, negative 1. So my graph is going to look something like this. Okay. And again, just like the exponential, you could certainly use the calculator to kind of get a good idea of the graph and some of the points, but just to see how it kind of works with this. With the 2 in front of the original problem, that would have been tough. So this is a more appropriate problem. So domain, how far left does it go? Well, it's negative 1 to infinity, because remember, it has to always be positive in the log. So x plus 1, which was in our log, means x greater than negative 1. Range for a log is infinite, so it'll be negative infinity to infinity. So now we've kind of talked about how we graph log and exponential. We can kind of talk about their definitions, so things like that. Evaluate the following expressions. So you could use a calculator, but you can actually do these without a calculator. I could obviously take this 3 up here. So this is the natural log of e to the third. Well, remember, natural log has a base of e, so really this is asking e to what power is e to the third. So e to what power will just give you e to the third? Well, that's simply going to be 3, because e to the third is e to the third. Log base 3 of 81 similarly is 3 to what power is 81? How many 3's do I need to multiply to get 81? 3 times 3 is 9, so 2 3's give me a 9, 2 9's give me an 81, so I need 4 3's. Log base 2 of 2 to the 9th is similar to the first problem. It is 2 to what power gives me 2 to the 9th? Well, again, all you'd have to do to replace your question mark is you'd simply have to plug in the 9 to get that. So this is going to be 9. And then finally, log base 9 of 17 is not a nice number, because 9 to what power is 17? I don't know. You could put this in the calculator if you have a handheld calculator. Remember, you have to do log of 17 divided by log of 9. But most of us are just using, Desmos or some calculator where you can type in the log with that given base. So log base 9 of 17 is going to give me approximately 1.29 if I round to 2 decimals. Okay, so 9 to the 1.29 will give you 17. Obviously, not accounting for some of the error in rounding. Okay, so we also talked about the properties of logs, where we have 3 main properties of logs, where we know log of x times y can be written as log x plus log y, or reverse. We know log of x divided by y is log of x minus log of y. And then we know log of x to the n is n log x, or vice versa. So you can go in this direction or you can go in this direction for these properties. So this first one says I want to break apart this log expression into the sum, difference, or multiple of logs. So I'm going to break it apart. So I'm going to have one log and I'm going to turn it into multiple logs. Now remember, I have this top divided by this bottom, so I can break this as log of r squared w7 minus log of x to the 10. So that's using the second property over here. But then I have two things multiplied, log of r squared and w squared. So I can write that as log of r squared plus log of w to the 7th, and then still log minus log x to the 10th. So I've broken them apart. I got that expression to more logs, but simpler terms. And then I'm just going to bring all my exponents down. Bring these all down to the front. So we'll get 2 log r plus 7 log w minus 10 log x. So most of the things we've done so far have been putting things together, but you can certainly break them apart as well, which will be helpful in the future. So the second one is a more common thing we did. We did it with equations, and we'll do it with equations here soon, where we're trying to make this a single log. So we have these numbers out front. So it's basically the reverse of what we did here. We'll kind of go from the bottom to the top. So we'll take these numbers out front and write them as powers. So we get the natural log of x cubed plus the natural log of y plus 1 to the 1/4 minus the natural log of x squared minus 4 to the 12th. Now when you're putting together and making it one log, just remember anything that is added or positive is going to go on the top. So x cubed will go on the top, y plus 1 to the 1/4 will go on the top, and then anything with the negative sign is going to go on the bottom. So x squared minus 4 to the 12th will go on bottom. So I turn many logs into one log. And again, if you recall when we did this with equations, it's equal to something and then we would use it to solve the problem. Sides. So speaking of solving equations, we have a lot of equations to solve here. So we're going to look at how we could solve these. So most of these we can use properties of the log properties, or we can try to use our idea of exponential and logarithmic definition. So if you have a log equation, so number 9 is a log equation, log base 3 of x equals 9. Now we would love to use the log property that says log of a equals log of b, and I could just cross these out and get a equals b. The problem, I can't do this in number 9 because there's only log on one side. So the way we do this is we get it to be one log on one side and one number on the other side, which we have, and then we will convert it to exponential form. So 3 to the power 9 equals x. And that would simply be my answer. Now if I wanted to figure out what 3 to the 9th is, I could. It would be a pretty big number, obviously. 3 to the 9th is 19,683. So that is my value for x. So most log problems will be like that, or you can get a log on both sides and you can solve it from there. Now 10 is an exponential, so 10, 11, 12 all look like exponential problems. So the first goal would be is can you get the bases the same? So if you can get the bases the same, that's great. You could just set the exponents equal. If not, like you can't get 4 and 5 to be the same, or e and 5, or 3 and 5. You can't get those to be the same. So our goal is to take the log of both sides of this. So log of 4, 2x plus 1 equals log of 5. Now the reason of doing this, of course, is I can now take this exponent out front. 2x plus 1 times log 4 equals log 5. Now, you've got a couple choices here. One choice is you could actually divide by log 4 and be okay because you only have one x. The more traditional way to do this so you can do all the problems the same is to distribute this. So 2x log 4 plus 1 log 4 equals log 5. So then what I'll do is I'll move everything without an x to one side, so I get log 5 minus log 4. Now recall, when you have log 5 minus log 4, when you have a subtraction of logs, you could write it as a quotient. So this is log of 5/4. Now, could you keep it as log 5 minus log 4? Absolutely. So then I want to get x by itself, so I'm going to divide both sides by 2 log 4. So my answer is going to be x is going to equal log 5/4 divided by 2 log 4. Now you can certainly find the decimal of this. This is the exact answer. Putting the decimal would just simply be putting it into the calculator. Now the only way I could have done this problem slightly different is I could have used natural log. It doesn't really matter. Any log you take is fine. We kind of said we love natural log when you have e, like the next problem, but if it doesn't particularly matter. But if you switch the both logs for ln's, it would work exactly the same. All right, let's look at 11. So 11, it's pretty nice because it does have the e. So again, we said if we have the e, it's nice to take the natural log of both sides. I didn't have anything to divide out. Remember, if there was like a 3 or something in front of here, you probably want to divide that out first, but there wasn't anything in this case. So we bring that down, so we get 2x natural log of e equals natural log of 5. And the reason the natural log and e go so well together is this is just 1. So in the bigger scope of the problem, you just get 2x equal the natural log of 5. So then to solve it, I'll simply divide both sides by 2. Natural log of 5 divided by 2. That is my exact answer. And again, if I wanted the decimal on the test, you could certainly give it to me. Now 12 is another exponential. Looks like our last exponential. Now again, I would love if I could get the bases the same, but I have 3 and 5. That doesn't seem like that's going to be very easy to get the bases the same. So if you can't get the bases the same, just go ahead and take the log of, doesn't matter which log, common, natural, does not matter. I'll go ahead and do the common log of both sides. So log of 3 to the x plus 2 equals log of 5 to the x. So we'll bring the x plus 2 down. X plus 2 log 3 equals x log 5. So now this is why I did the other problem, the problem 10 this way, because in this case you have to distribute. You don't really have a choice of dividing out. So I just like to do all the problems the same way if I can. So I get x log 3 plus 2 log x, or 2 log 3 equals x log 5. So now if you notice, I've got 2 terms with x and 1 term without. So I'd like to get everything with an x on one side. So I'm going to subtract x log 3 from both sides. So I'll get 2 log 3, and I'm getting log 5 minus log 3 both with an x. Well, remember, if you subtract logs, we write it as a quotient. So it's log 5/3. Because when you subtract logs, we always write it as a quotient. And then I can simply divide both sides, 2 log 3 divided by log of 5/3. Now, could you simplify this more? Sure. Could you make the top log 3 to the second, make it log 9? Sure. But as long as you have it in a form where the x is by itself, generally that is acceptable. That's really what we're looking for on these types of problems. Now our last two are log problems, and they're kind of distinct log problems. You can notice the first one, only 2 things have logs, but the second one, every term has a log. So and the first one is a very common problem. I find a very high probability this would be on your test. If you have something like this where only some things have logs, the idea is let's get everything with a log on one side and then a number on the other side. So we get log base 8 of x plus 2 plus log base 8 of 2 equals 2. Now the reason we get them on the same side is now we can use our property and we can make this log base 8 of 2 times x plus 2 equals 2. Now we can't just get rid of the log, we can't just cancel it because we don't have logs on both sides. So our idea is we'll take this base and we'll switch it to exponential. So we get 8 to this power of 2 equals 2x plus 2. Now the nice thing is this works out to be a linear equation, no quadratics, so we just solve it. 64 equals 2x plus 4. I'll subtract 4 from both sides. 60 equals 2x, so x equals 30. Now, I should check it and make sure that it makes the logs positive. Remember, if you plug it in and you get a negative log, that's bad. 30 plus 2 is, of course, positive, so that's fine. A lot of times when you get quadratics with this, that is where you can have some issues. All right, finally, let's look at our last equation. Obviously, a lot of log and exponential equations. These are pretty important for your test. This one, everything has a log. So if everything has a log, I'll still have to put it together. So I'll get log, natural log of 3x plus 4. I'm going to take that half up top. Remember, when you take a power of a half, that really means square root of 4. That'll be important here in a second. So nothing else in front. Now these two logs are subtracted, so I can write that as 1 log divided. So natural log of 3x over 4 divided by 2, because again, the square root of 4 is 2, equals the natural log of x squared plus 5x. So now we have 1 log on each side. This is very different than the problem we just did on the left, number 13, because that one, not all the terms had logs. Since all these have logs, I can just simply cross it out. So I get 3x plus 4 divided by 2 equals x squared plus 5x. So I definitely have a quadratic because I have a square. So I'm going to multiply both sides by 2 just to get rid of this 2. So I'll get 3x plus 4 equals 2x squared plus 10x. And then since it's a quadratic, I'm just going to get everything on one side. So 0 is going to equal 2x squared plus 7x minus 4. That's simply just taking the 4 over and the 3x over. Hopefully this factors, and it does. You can go back to your factorization or use quad formula. This is going to be 2x, and it's going to be positive 4 and x minus 1, because that's going to give me my 8 minus 1. So my two solutions will be 1/2 and negative 4. Add 1, divide by 2, subtract 4. But if you look at our logs, I can't put negative 4 into this log, because 3 times negative 4 is negative 12. Negative 12 plus 4 is negative. So I definitely can't have negative 4. I can't plug it in and make my log negative. Now, as far as the 1/2, 3 times half plus 4 is positive. Half squared plus 5 times half is positive. As long as you plug it in and get a positive, even if the x is a negative number, as long as you're plugging it in and get a positive, it is a valid solution. If you plug into any of the logs and get a negative, it is not a valid solution. It's what we call extraneous. All right, our final problem is about compound interest. So this one says an employee receives a 5% raise each year. They currently make $125,123. How long until they make over $1 million per year? So this is obviously a compound interest problem. Now the interesting thing about this compound interest problem is it says annual raise, right? 5% rate each year. So our raise, our N, is only going to be 1 because we're only getting that raise, that percentage, 1 time a year. Our T we don't know. We want to know how long it's going to take. Our principal, our current starting amount is $125,123. Our rate is, of course, 5% because that's the percent I'm getting every year. And our A, I'd like to get to $1 million. So $1 million is what I'd like to gain to, right? So this is using the compound interest formula. Sometimes we like the continuous compounding one a little better, but this one's fine. So I'll plug in some numbers. So I'll get 1 million equals 125,123. 1 plus 0.05 over 1 to the 1 times t. So kind of a weird problem because it's only 1. That'll give me 1 million divided by 125,123 because we want to get that exponential term by itself. And that's just 1.05 to the t when I simplify that out. So now, just like all these problems, I can't get these bases the same, so I'll take the log of both sides. So log of 1 million over 125,123 is going to equal t times the log of 1.05. And so to get t by itself, I'll simply divide out. So t is going to equal the log of 1 million divided by 125,123 over the log of 1.05. So since it's annual, there's not a lot of tricks to this problem. So with this 5% raise, if I put this in the calculator, I am getting about 42.6 years. So their salary will increase from, $125,000, which is a lot of money, to $1 million in 43 years. They just got to stick it out for 43 years, and they'll make $1 million. So these are just a small sampling of the problems. I suggest you look at these problems, look at your notes, look at some of the examples we did in class. We'll practice more problems as well before we take our final test of the first semester.